Liquid Nitrogen Day. Alright, so a little bit of fun, a little bit of learning today. We are going to mess with liquid nitrogen. It'll be a little bit one of the longer videos, but it's worth it. You should enjoy this one. So this is a Dewar Flask. Actually, let me lower this down a little bit so you can see the whole flask. It holds 10 liters, which 10 liters is about 2.5 gallons, right? So if you imagine a gallon of milk, this is a lot bigger than 10 liters. The reason for that is there's a layer of styrofoam about this thick all over the inside of this thing. Liquid nitrogen is not real hard to make, but liquid nitrogen is difficult to keep, right? Because it's very, very, very cold. So the environment is really warm. So it's like you've got, imagine if you were trying to keep water and everywhere was 250 degrees Celsius. Well, everywhere it touched, it would be trying to boil that water, right? So it's the same thing here. According to the liquid nitrogen, the room is incredibly hot. So we're trying to cut the liquid nitrogen off from the room, right? So we've got all the styrofoam around it. It is not a seal-on cap. You notice this just kind of sets in and out of there. If we think about that, it might be like, oh, well, you should get a nice screw-on cap so it seals it in there like a Diet Coke does. But as we did that, as energy did leak into the liquid nitrogen, it would boil it, raise more and more and more pressure. Pressure inside a closed container is a bomb, right? So that's not, we don't want big boom, right? I know you want big boom, but I don't want big boom, right? So it even has a little weak spot here. If you look on the side right here, right, that's a weak spot so that if it were to somehow get sealed, it has a weak spot so it gives there and it would vent out here and not big boom everywhere, right? All right, so we're gonna go ahead and pour some of the liquid nitrogen into our magic liquid nitrogen holding container. This is a very high-tech container made out of some very high-tech styrofoam. It's just big styrofoam. So this will hold it reasonably well for an hour. A good quality Dewar Flask can hold it for like a week, right? So that works pretty well. Whoa, that's rattly. So anyway, we'll go ahead and pour it here. You can kind of see it's basically just a colorless liquid. Outside of the foam, the smoke stuff rolling out of it, it really looks like I'm just pouring water. The smoky stuff coming off of that is water vapor. So the liquid nitrogen is in here boiling now. Nora, can you walk here, I'll walk this over. And maybe we'll put this in so you can see it a little bit. I don't know how you can see that. It basically looks like a tub full of water. If I breathe into it, it does that. Here, well, kiddos, you go ahead and do it.
Oh, Jesus.
Yep,
Oh,
pretty cool. Okay, we'll get a chance to mess with it.
Oh, that's cold. It's really
So as it sits in here, the liquid nitrogen's really cold. At first, it really steamed up a lot because it was trying to cool off the styrofoam, but the styrofoam, it got that cold now, and it'll set in here pretty nicely. But if you introduce some moisture to it, it's going to basically make little tiny snowflakes, right? Because the moisture coming out of my lungs is pretty high temperature. If we get it really cold really quickly, it'll basically make little tiny snowflakes. So what you see here, that's not liquid nitrogen. That's actually just like a fog, like a little tiny snowflakey kind of thing. Okay, so Fredlings, go ahead and grab your balloons and bring them up. Okay, so you're going to put those in there. Before you do, how are the air molecules in those balloons moving right now? Are they moving fast or slow? What do you think?
Probably pretty fast.
Pretty fast, yeah, they're moving pretty fast. If we put them in a cold environment, how are they going to want to move?
Slow.
Slow. And since the air's squeezing on them a whole bunch, the air's squeezing right now, but the balloon's pushing back. If we slow the inside molecules down, what's going to happen to the balloon?
They go boom. No, it's
not
going to shrink.
It's going to shrink. So go ahead and put it in there.
I want it to go boom.
Go one at a time. Push it down. So it is. It's going down.
Okay, I have to give one to Nora.
No, it's fine.
Woo.
Look at it.
Hey, you're next.
Yep, so you push them down. If you push them down under the liquid a little bit, it'll work even better. Some of the gases in there will condense easier than others, right? But we're seeing the volume on them shrink. I've got a little banana in here while they're shrinking balloons. We'll put a little banana in here. Just one of those will, and that'll be plenty. Well, it's for kids watching at home, it might not be the most exciting to see balloon after balloon. Yep. We get some liquid nitrogen on top of them. So you can put your hands in it. You just don't keep your hands in it a long time. Careful, your hand's getting real close there. But yeah, so if you touch, your hands are really hot, so they'll boil the water around it. No, don't just do it on your own. If you want to touch, take your hand and make it straight like a knife, dip in and back out.
Whoa.
In and back out, so you don't freeze your fingers. Going a little further, yeah.
Oh.
So that it's dry, you'll notice, right? Yeah, your hands are really hot, so they cause it to boil around your hands. I did put a banana in here while they were doing that. And then let's go ahead, go ahead and take a balloon out. And then set it on the table. Yeah, go ahead and back up so you can see it. Move them around a little bit. Don't leave them in one spot. They'll pop. If you leave them in one spot, if you move them around, then all the plastic gets to warm up. Put it down, Robert. If you don't put it down, it'll pop. You got to move it around a little bit so that the plastic doesn't all, because if the plastic is frozen, don't worry about the banana. Oh, I'll grab the,
It's boiling.
yeah, the banana's hot. If you ask the liquid nitrogen, right? The banana's hot.
Whoa.
So this guy did rip in one spot, but as that warms back up, then those gases want to move around more and all that kind of stuff. That's liquid, into a solid. So when the CO2 turns into a solid, because it doesn't have a liquid state, so it'll go straight to a solid. So when we pick it up and move it around, you can see the nitrogen is a liquid, oxygen will be a liquid, but the CO2 that's in there, no. And as I pull this one out, as I pull this one out, I'm going to try and hold it up so you can see there, but there's actually the stuff that's inside there. There's liquid floating around, right? It's cold enough that the nitrogen turned into a liquid and the carbon dioxide actually turns into a solid, which you can sometimes see in there a little bit. One of those things that's definitely easier to see in person. Will, be quiet, or you're going to get kicked out of the video. Right? So if you keep the plastic from getting too brittle, it can warm back up and be just like it was before, right? And since there's oxygen, nitrogen, and CO2 in here, when we freeze it and get it really, really cold, all three of those turn into, well, two of them turn into liquids, and then the carbon dioxide doesn't have a liquid state, right? That's dry ice, so it turns into a solid.
What happens if you put it back in?
It'll shrink back down again and stuff, right? So so that is, if we think gas laws, right? We think volume and temperature, what we're playing right there, right? So what's our gas law there? I didn't hear you. Say it one more time. That's Charles' law. That's right. That's Charles' law that we got to mess with there. Now we're going to mess with pressure and temperature. So what I'm going to do, burn my hand is what I'm going to do, is I'm going to put a little bit of liquid nitrogen in here. I'm going to set a stopper on here. I'm going to make a sealed container with a weak spot. If I increase the temperature and it's a fixed volume, the pressure is going to go boom. Pressure is going to go up. Yep. And when the pressure goes up, that's going to turn this into a projectile. So we're going to put a little bit of liquid nitrogen in the bottom of our test tube. Right. We've got liquid nitrogen in the bottom there. And then we'll catch it. Toss it back.
Scary.
Well, my depth perception was not great there. Okay. So a little bit more. And we'll go. That was too quick. Too quick. Need to punch it down harder so it has to build up a little bit more pressure. Oh, come on. I can usually get it to like the second or third row. Oh, that was really weak.
Can I try?
All right. Yeah, you want to try?
Yeah.
Take this, scoop up a little bit. Don't keep your fingers down there a long time. Yep, scoop up some. Oh, you got to scoop up a little more than that. It's okay. Got some in there?
A little bit.
Okay.
Woo! That's pretty good.
There you go. Don't keep your hands on the part that's liquid nitrogen very long. Okay. So we'll and a golf ball. So a racquetball, right? So racquetballs work by a couple of things. One, you've got nice elasticity to it, right? It's got long chain polymers that are laying next to each other. So this is how you can get London dispersion forces that are strong, right? You have these long chain polymers. But those long chain polymers get help, right, from bouncing back by the gases inside. So we're going to do two things. When we get it cold, those long polymers will get rigid, and then the gases that are inside this won't push back, right? So we'll go ahead and put that down in the liquid nitrogen. This is a golf ball. Golf balls are a little different. But we'll go ahead and put a golf ball down in there. They take a little longer. What did you have? Ping pong ball. Oh, you got to show this. This is awesome. The ping pong ball is just straight up rolling. Oh, it stopped. It was just full on it was in a full spin mode as it was getting colder, I guess. But well, that guy will take a little longer too because he's floating. Right? Since we've got the banana right there, and you just saw the banana. Banana was nice and soft. Now, banana's a little hard. So since the banana's a little hard, I don't know why. Our banana was weak. Banana was brittle, right? So it's nice and hard. They are more brittle now, but you can, if you get a good enough start on it. Hammer a nail in with
What does it taste like?
with banana. You want to try a little bite?
Sure.
You have to do a small bite because it is really, really cold. But what it tastes like is kind of freeze-dried banana stuff.
Oh, yeah.
Take if it's a small bit, you can take it.
Freezing.
Yeah, just take a little bite and eat it, and then tell everybody how it tastes. Come back on camera and tell everybody how it tastes. Yeah, you want a little piece.
It's cold.
Yeah, it's cold.
Froze to my
But
tongue.
once you warm it up, you can taste the banana and stuff. It tastes a little bit like almost
it
like
froze to my tongue. You monster.
So anyway,
All right, so that racquetball we had in here, right? We are going to take her out now. And before, remember, it has that elasticity where it would bounce and it's all nice and neat. And go ahead and kind of point it downwards a little bit. There you go. And I'm going to throw this little high in the air.
that sound amazing.
And now it's all little tiny pieces.
Oh, golf ball's done.
Golf ball just exploded.
Will, scooch.
Yeah, you can.
Go. Let's go ahead and pick it up out of there.
I'm not sure if it caught the.
It's fine.
Okay, so there's inside of a golf ball. If you did know, or you. Oh, jeez.
It sounds like a marble, right?
It does sound like marble. Yeah, that's what it's for.
Yeah, so the outside just shrinks faster than the inside does, so it builds up pressure.
Now, Easter is over, but I have all these delicious peeps. Like, I don't know, I really want to save them for next year, right? So let's think Captain America style. Let's freeze them. Let's freeze them. Beautiful flowers from my husband, right? Same concept. I want these to last forever. So let's just freeze them. Now remember, you're in biology with Mrs. Higgins. Plant cells are different from animal cells. Why? Cell wall. So think about what's going to happen when you just completely freeze this cell wall, right? Cell walls are pretty sturdy. They're pretty rigid. They don't really want to break down. They don't want to go anywhere. But now when you freeze it, oh, that is cool. That was cool. That was cool. That was cool. The cell wall are totally going to collapse. Like the cell wall's not going to be there. So I'm going to keep one actually out. Should we do the big one?
Yeah.
I'm just going to let it sit there after it freezes so you guys can see this best you can. Oh, that was cool. Yeah, if I had this at my house, I would freeze all my kids' toys. Give it some more water, it's still living, right?
It's doing great. It'll be fine in 5 minutes too.
I think the peep is good.
Yeah, I bet.
I don't know how you're doing that.
I
drop
burn myself occasionally. No, I hit the peep with a hammer.
We're going to hit the peep with a hammer. Now, I want to save this, right? So now we're in 2021. Like, happy Easter. I really want to try to keep my peeps again. Yummy, 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 yummy. But I want to share it, right? So I'm going to share it with all of my friends.
Try it. Grab a small piece, kiddos, and try a bite. Again, a small piece, and tell me what it tastes like. I know. Especially right at first. Kind of like a freeze-dried marshmallow, like Lucky Charms. If you think like Lucky Charms
good.
marshmallows.
That's good.
Yeah.
They're better freeze-dried, honestly.
Yeah, so it locks up all the moisture. So I always think they taste a lot like
One for you, and one for you.
Yay!
So I have a different balloon now. This is a balloon of oxygen, and we're going to put the oxygen down into this liquid nitrogen environment, but I don't want the balloon to freeze off. So Jack, go ahead and take over holding it for me here. Try and kind of hold that and keep it down there in the tube. So oxygen is we're able to liquefy oxygen with liquid nitrogen for two reasons, right? See if we can think about the two reasons. First is Graham's law. Which is bigger, nitrogen into or oxygen, if we think mass-wise, right? Oxygen's bigger, so that means it moves slower. If it's moving slower, it's going to be easier to turn it into a liquid than nitrogen is. And because it has more electrons, if we think London dispersion forces, more electrons means stronger London dispersion forces. So you can get liquid oxygen, or you can get oxygen turned into liquid oxygen with liquid nitrogen, but not the reverse, because liquid nitrogen's freezing point is actually boiling point is lower than oxygen's, right? So as we can see, keep it in the liquid nitrogen. No, don't have to move it around, just keep it there. That's okay, the stuff's not gonna cause it a problem. So as we do this, it's gonna, the balloon will continue to slowly get smaller as we turn it into liquid oxygen. And Jack, you were asking a question right before we started.
Yeah, so can we like freeze a marble or something?
Yeah, so the deal with a marble and a lot of things, like students a lot of times will ask about like, oh, what about my pencil? Because it's handy, right? So a lot of things aren't that fun when this is already frozen. So can we freeze it? Sure, it's already frozen. Is it gonna change a whole lot? Some things, if they have some structural integrity issues, will crack and break and that kind of stuff. The golf ball, the outside froze quicker than the inside did, right, or shrunk quicker than the inside did, so that builds up pressure and it'll break. But most things aren't all that interesting. But if you think about things that have a lot of moisture in them, like flowers, or you think about, or peeps, or things that are flexible, those tend to be the things that are more fun to freeze, right? People, yep. So if you freeze a person, then you rupture their cells, and so it's hard to unfreeze them. So Austin Powers or Captain America or whatever, probably not the most realistic science movies we've ever seen.
Captain America's not real?
I know, it's shocking, isn't it? I thought it was 100% real. I say freezing, I should say condensing, because going from a liquid to a gas is condensing, not freezing. Let's talk about fire, because fire is fun. So we saw in the lab the other day, carbon dioxide puts fires out. It's not the only, can we see the flame even on that? It is not the only gas that will put fires out. Nitrogen will put fires out just fine too. There is nothing magic about nitrogen that puts fires out, nothing magic about liquid nitrogen. It's not because it's so cold, but as I am putting it into the nitrogen environment, right? This environment that the match is in right now has lots of oxygen. But if I put it down here, it doesn't have the oxygen, so it snuffs the flame right out. This guy, I'm going to try and increase the pressure and get that liquid oxygen to liquefy a little quicker. Yeah, one of the cool things about liquid oxygen is it's blue. There's some cool electron transitions that go on in oxygen that are beyond what we need to worry about. But the electrons, basically if you think Boyle's law, pressure from gas, Bohr, and Bohr's model of the atom with the electron transition stuff, the electrons bouncing from one energy level to another, we can get that blue color from our oxygen. So our oxygen has been turned into a liquid, so we can see the balloon's all deflated. Yeah, go ahead and light it, you're fine. It'll take you a second to get it lit. So if I take this off, now what's going to happen is the environment is going to warm that up, and it's going to start boiling again. Go ahead and pass the match in front. Don't put your fingers right in it. Pass it in front of there. Whoa, you see. Put it in and out. Go in and then back out. Keep going back and forth. And then back out. So you see as it goes into the oxygen-rich environment, it's able to burn a lot faster. In our next unit, careful, you're going to burn your fingers. Go ahead and get it relit. Or a different one lit, not relit. In our next unit, one of the things we're going to talk about is increasing concentration will increase concentration rate, right? So you'll have an excuse to go back and watch this video. This time, go ahead and drop it down in there. Let's just see what happens.
What in the world?
So it is burning the match just fine down in there. Now that wood takes a minute to burn, but there was plenty of oxygen in there, so it was able to burn the whole match. If you look, there is no match inside there anymore, right? I know, right? You think it's so cold it would put the match out, but there's still a ton of oxygen in there, and the match has some energy, so it does just fine there. It's all gone, right? Our oxygen's all gone. I know it's sad. I know. I want to keep burning things too. Go ahead and put it down in the nitrogen environment. See, it doesn't do the same, right? In the nitrogen environment, it puts the flame out because there's no oxygen there to support combustion. Let's go. You're good.
Our ping pong ball in here is pretty cold now, so we're gonna see. Get a little bit colder. We can just take this sucker out. A little bit of force. Whoa. Made the sound. It shattered. It just didn't go everywhere.
Well, hand it to me.
Rubber tubing. Okay, we're gonna try this one. This is the stuff that you guys use when you hook up your Bunsen burners, right? So it's just this hollow rubber tubing. Shouldn't take too much. We're gonna try to put that end in there as quick as possible. That does not take long. I'm so timid for this. Now, those of you that are sitting in the front. Woo! Oh my God! This is Higgins' first time too. This is fun. Oh my gosh, it's like noodles. Then it's just like.
Can I eat a noodle? You said it was noodles.
Did it warm up enough already? Here, we can throw one in there. Smack it with a hammer in a minute. No, you can't eat that well.
Oh my gosh. Like this is why you. Oh, see that one was sitting out a while. This is why you use safety goggles.
Yep, a lot of those things that are naturally flexible have a nice glass transition temperature. It varies, but you get them cold and then they just get brittle. Go.
All right, toss me Captain America.
Captain
mold.
America's coming to save the day.
Captain America mold. You know, you can freeze and then you're gonna relive later in life. Oh my gosh. Oh. How long was he in there?
50 years,
Was it
something
50?
like that. 50 years.
Yeah, something.
His cells are doing fine. It's fine to freeze for 50 years and then
We're
thaw
gonna let him
out.
freeze in there for a little bit. Sponge. We're gonna try a sponge. Just going. Oh. Okay, the sponge is pretty cool. Can you poke it like that? Really? Oh, now it's not getting. It's getting there a little bit more. So true. Write our name in it. Yeah. Oh, that's pretty cool. Don't see that every day. American mold.
You need to go and stick it over.
It's like a pancake. Cook it on one side and then cook it on the other.
Whoa, dude!
Can I touch it?
No.
Whoa, look at that.
Stop! I want to. No.
It's like eating a cracker.
Look.
Can't wring it out. It's like back cracking. Chiropractic, right? Ready? All right, let's try Captain America mold. Oh my gosh. Ow, ow, ow.
Gosh.
Look at that! I don't even know if he's gonna. He's just gonna crush.
Give him a massage.
Of all the things we put in the liquid nitrogen, he held up probably the best.
So I mean, it's true then.
I guess
right?
it
It's
checks
gotta be
out.
true.
Checks out.
Mole cells, animal cells, we're animal cells, right? It's true.
So a story I was told, I don't know if it's true, but a story I was told when I was in undergrad was that a lot of top research scientists that have top secret labs don't let custodians come in to clean it. So since nitrogen is nonpolar and dirt is nonpolar, to clean the floor, they would just take some liquid nitrogen and throw it out on the floor, and it picks up all of the dirt and send it to one spot.